like introduced, my name is Sung Mo Kim. My advisor is Carl Dietrich. And my dissertation topic that's penetrating my PhD study, that's spectrum sharing. So as you know, there have been a lot of wide variety of different spectrum sharing problems among multiple bands. And among them, I studied 3 different spectrum sharing problems in 3 different bands. And one of the 3 was 3.5. And the other 2 are actually 5.9 between DSRC for B2B communications and 802.11ac, which is one of the high-speed Wi-Fi standards. And the last one that's what I'm working on right now, it's 70 gigahertz millimeter wave for 5G. So this is one of the things, and I'm open for further discussion about spectrum sharing if you have any interesting problems or some necessity of collaboration or things. I'm happy to discuss them with you. So this presentation, like I said, is about 3.5. And I remember that was initiated by the FCC around the end of 2012. So that time I also started this, and my own study has also been, evolving accordingly with the FCC's discussion. So for the first time when I was starting this research, I was just considering a coexistence between a generic OFDM system and pulse radar. But as the discussion around the FCC has been going on, they are starting to focus on LTE because IEEE 802.11 work group, they got out of this discussion because they found that this band is too much restricted around the rules and getting out of the spectrum when the radar comes in. So they were unsatisfied, so they got out of discussion. So LTE is now pretty much the only candidate application by applying this 3.5 spectrum sharing rule. So now my research also has been nailed down to LTE, and I am interested in interference. There can be 2 directions, right? From radar to LTE or from LTE to radar. And my interest is from the interference from radar into LTE, assuming that the LTE to radar interference is controlled through, number one, the cellular system is better for coordinating itself for reducing the interference. And also, we can assume that the 2 systems, radar and LTE, can be separated far enough for reducing the interference toward the radar. But the radar has a way higher transmission power, so I was assuming that it's way more likely that LTE is victimized in that kind of spectrum sharing system. And recently, the FCC and actually WinForum, one of the standardization organization, they included a mediator entity in the coexistence framework architecture that's named Environmental Sensing Capability, ESC. So that's actually in the middle, right here, just like a light point, right here. And whenever a ship or radar comes in through across the shoreline, then it detects by spectrum sensing, and it informs that approaching radar to the coexisting LTE system for emptying, for kicking out the LTE system, during which the radar has to operate in that band. So that's the architecture, and I'm going to be working on, in this talk, I'm going to be talking about that spectrum sensing capability. So basically, the proposed OFDM scheme is that it's a combination of a technique that is called pulse blanking at the receiver and pre-coded subcarrier nulling at the transmitter. So that's the proposed pair of OFDM scheme. So the starting point was, so pulse blanking, because radar signal has way higher interference power than a digital communication system. So even if you receive it from several tens of kilometers away, then it's still very high in terms of amplitude on time domain. So the one of the most efficient way of reducing that interference power is to cancel that time samples, and then you put this time OFDM symbol through FFT at the receiver. So by doing that, in fact, you are able to reduce a lot of ICI, intercarrier interference, in an OFDM system. I found that. So I started from there. So pulse blanking is not a novel technique. That's there. That has been famous of being capable of reducing high power pulse interference in the field. But I found that still pulse blanking leaves a lot of intercarrier interference. So we needed something more. And I wanted to put some additional burden at the transmitter because it's a downlink. So that was the starting point. So then why pulse blanking leaves intercarrier interference? That's Fourier transform, OFDM. So this is an example, either real or imaginary domain of QPSK on the axis, because that's why that has both ones and zeros. So QPSK, 64 FFT on the time domain. That's the red signal. This is an OFDM symbol. And assume that you, at the receiver, you apply pulse blanking on 2 time samples out of 64. Then the impact spreads over all the subcarriers. That's the thing, because I skipped the FFT definition formula, because FFT is a one-to-all mapping. So every single, for example, time domain sample contributes, and one time domain sample contributes every single frequency domain sample when you Fourier transform it. So that is the thing. So that's how ICI is introduced even after pulse blanking. But if you didn't pulse blank those 2 samples and leave as very high power radar signal, then the ICI would have been worse. So that's how you can reduce the ICI by applying pulse blanking, but also that's how you still leave some ICI after pulse blanking. So I started from here. So I actually tried multiple techniques, but I have some restriction because I was also only interested in transmitter. So I was interested in some pre-coding techniques or something like that. But I ended up finding that the technique that is called interference self-cancellation, which is one of the most aggressive techniques that enhance error rate by sacrificing data rate, was working fine. And actually there are multiple different types of ISC techniques so far that are suggested in the literature. And I ended up finding that instead of any other redundant subcarriers, inserting null tones between the data tones, that's the most effective, as you can see here. So this is the very first simulation results according to different pulse duty cycle. And PSUN, my pre-coded subcarrier nulling, PSUN, my technique, is shown to outperform the other types of ISC techniques. And the main reason is PAPR. So for analyzing the reason, I generated an example signal. So the blue one, sorry, it's not. So this is the lower one, that's frequency domain signal. So I allocated 3 ones in the middle out of 64 subcarriers, and that is the upper one is an OFDM symbol on time domain. And at the receiver, I received that signal in two different scenarios. So scenario number one, that's on the upper side. So I applied pulse blanking in lower amplitude area on purpose to see the impact. And this is the ICI. And scenario number two, I applied pulse blanking in the high amplitude area. Then you can see the ICI becomes way more severe. So the message here, what we need to do is to reduce the level of fluctuation on time domain when you transmit a OFDM symbol and receive it and apply pulse blanking for reducing the radar interference. So for doing that successfully, you need to reduce the fluctuation level on time domain at the receiver. So again, back to interference self-cancellation. So by reducing the number of actually having energy, so in here, PSUN, by reducing inserting null tones, you can reduce the number of actual energy subcarriers. So by doing that, you can reduce PAPR, and that's the main reason that you can outperform any other self-cancellation techniques. So by the way, I forgot to mention. So interference self-cancellation technique to introduce, that's a frequency domain redundancy inserting technique. So if you have, for example, look at this data conversion, then, for example, subcarrier number one, you have one, then subcarrier number two, it's a negated version of that. So you allocate data tones on the odd numbers of carriers, and the even numbers of carriers, that's a negated version of it. And there's another version, for example, symmetric data conversion, that's the same thing, but in a closing door manner from far to close. And you can wait, or you can allocate some frequency, or you can take a conjugate. So there are multiple ways, but I found that for this type of interference reduction technique, allocating null tones is the most efficient way. So, as I explained right now, not only for PSUN, but also for all the interference self-cancellation technique, it's sacrificing data rate. That is a big problem. Right? So we need to compensate that as much as possible. So specifically in this problem, I found there can be some ways. So the ways that I found are two. So for minimizing the data rate loss, a transmitter that applies PSUN, that techniques, allocating null tones between the data tones, that transmitter performs the following two steps before actually transmitting that OFDM symbol. So number one, that transmitter applies PSUN only at the OFDM symbols that are estimated to be hit by radar interference. So you need some more knowledge for doing that. And that a priori knowledge is provided by the SAS, Spectrum Access System. That's specific only for this 3.5 gigahertz spectrum sharing problem. So this might not be applicable for other spectrum sharing problems, but recently, as far as I know, database is very popular as a mediator in most of the spectrum sharing problems. So it can be applied in a different name or a slightly different way, but the thing is, the message is a priori information is likely to be available in spectrum sharing problem because that's what people are finding by now. And so that's provided by the SAS database, and that information is created by the ESC, which is the sensing capability we saw in the first page. Right? So that device senses the spectrum and it detects some interference. And that provides that information to the central database, which is SAS. And SAS is responsible for informing the cellular system about the incoming interference. So that's number one. And number two, so that transmitter, assuming that, no, not assuming, finding that PSUN is also efficient in suppressing Gaussian noise. So we replaces PSUN, we replace the channel coding with PSUN at the OFDM symbols that are estimated to be hit. So all the other symbols that are not estimated to be hit, they are just the same. Convolution decoding, turbo coding, just the LTE, and you leave it because it's not very frequent. But the OFDM symbols that are estimated to be interfered, then we do these two things. That's the protocol that's specific in this coexistence problem. So then now we have a pair of OFDM system at transmitter and receiver. So in that way, so we saw that it can suppress the radar interference. And that architecture, that OFDM system, relies on the information that is created by spectrum sensing. So now we're curious, then what if that information is not 100% accurate? So we need to analyze. We wish to have some framework. Then, if we control or if we, calculate that information's reliability based on some known techniques. So I applied the popular Neyman-Pearson detection theory to the ESC capability device. So hypothesis 0, that's Gaussian noise floor. And hypothesis 1, that's interference signal. So a false alarm is defined as a situation where an OFDM symbol is declared to be hit by radar interference, but in fact it's not. So PSUN was used for an OFDM symbol, but that OFDM symbol in fact actually goes through a Gaussian noise, a more favorable environment. And this detection is the other way around. So an OFDM symbol is declared not to be hit by interference, but actually it is hit by interference. So in a higher level translation, we can say that because radar interference is far severe channel impairment than Gaussian noise, we can say the false alarm is an overprotection. You didn't actually need to do that, but you did based on the wrong information, false information. And this detection is under protection because that is in fact hit, but you didn't protect that OFDM symbol by PSUN, but just leave with channel coding. So by applying that detection theory in this spectrum sharing framework, that's based on ESC, then you can have this higher level understanding about false alarm and misdetection between the radar interference and Gaussian noise. So based on this framework, now we have the OFDM system, TX and RX, and a framework for analyzing the imperfect pulse prediction by the sensing capability. Now we perform some MATLAB simulation on that, and I borrowed LTE parameters for LTE and for the OFDM system and the radar, because both radar parameters are offset. So I was trying to generalize the parameter, but for the easiness sake, I use pulse repetition time 1 millisecond, which is synchronized, which is identical to 1 subframe time of an LTE standard. So we can easily measure the radar interference within the LTE in a synchronized way. And so this is the first set of the result, and I'm afraid it's not very clear. So the y-axis data rate, throughput, megabps, and the x-axis, there are 2 values. The first one is bit energy to noise spectral power density, and the other one is duty cycle. So because I set for the left figure, I set the duty cycle to 0.1. So as the SNR becomes higher from 0 to 12, the relative dominance of pulse duty cycle becomes higher. So the message that I want to deliver from this slide by these 2 parameters are the relative dominance of pulse interference compared to the Gaussian noise. Then we can find the message that outperformance of PSUN, the OFDM system equipped with PSUN, increases as the dominance of pulse interference gets higher. So the blue dots is indicate the performance of an OFDM system that's with the pulse technique, PSUN, and the red dots that's without PSUN, so only with convolutional coding. So that's the message. So based on these 2 metrics, we can see that outperformance increases as the interference gets more severe. And this set of results indicate the impact of imperfect sensing. So we have false alarm probability and misdetection probability. And obviously, as either false alarm probability or misdetection probability increases, approaches to 1, the outperformance disappears. And that converges, the performance converges into that of the system without the technique. So that is the thing. And you can see, but it might not be very, a major thing. But you can see, according to false alarm, it decreases, in this way, kind of slower. But this detection, it decreases faster. And the reason is that, like I said, false alarm is overprotection, and this detection is an underprotection. So that's why, more misdetection you have, it's the performance is decreasing faster. That's the reason here. And the last thing, because it's almost impossible to to parameterize the occurrence of pulse interference. I wanted to generalize that quantity. So rho here, that's the probability of pulse interference within a subframe time. So if it's 0, then there's no pulse interference within your LTE subframe time. If it's 0, you see a pulse interference every single time, every single subframe in your LTE simulation. So I wanted to generalize that quantity which is necessary by a certain parameter that's normalized into 0 to 1. That's that quantity, rho. So that also represents the dominance, the CBRT of pulse interference in the channel. So as you can see also, an OFDM system that's without PSUN decreases faster as rho increases. So the main message through this talk is that, so we discussed an OFDM system that's being more robust against pulse interference, and which is applicable for 3.5 LTE. And also, in addition to that, we discussed a framework for calculating imperfect sensing prediction based on ESC, which is suggested in the 3.5 LTE standard that's finalized recently. And now I'm seeking for some proper applications. So because LTE uses now carrier aggregation, 3.5 is not the only spectrum choice for them. So they are likely to be aggregating multiple bands from multiple spectrums. And that 3.5 chunk will be one of them. And I want to extend some discussion to something like, because as the spectrum bands are being diverse in the future, and also the applications are being diverse too. So LTE is now being applied for even V2V communications or D2D communications. So those applications will be can be a candidate for this new spectrum resource that has this unique feature under presence of interference. So that's the direction of extending this discussion. So if you are interested or if you know something, and please find me and talk to me. I'm happy to do that. So this finalizes my presentation. And if you have any questions, comments, suggestions, let's talk.